So welcome to my YouTube channel. So today I am going to solve the MSc Entrance exam problems of 2024 IISER Kolkata Entrance test. Okay. So I'll make two videos. One video is for algebra part questions and another one video is for analysis part question. Okay. So this is the first part question. I'll upload the both part together. Okay. So this is the first part. It's algebra section. So the first question says that let G be a finite group whose all proper subgroups are cyclic. Justify if G is a cyclic. So the one of the obvious example, the first non-abelian group is S3, right? So S3, order of S3 is 6. So then any proper subgroup of S3 must have order 1, 2 and 3, right? So subgroup of order 1 is trivial subgroup, which is obviously cyclic, and any subgroup of order 2 and 3 is also cyclic because the order are prime, right? It's a prime order. This will imply that but S3 itself is non-abelian, not even abelian. Okay. Part 2. That means S3 is one of the counterexample. You can give Q8 also. That also works. And you can make any other example also. Is Q plus finitely generated? Let Q plus be finitely generated. Okay. And it is generated by, say, 1 by B1 up to an by Bn, right? Let B equal to 1 by, sorry, not 1 by, let B equal to product of all the denominators of these generators, okay, B1 up to Bn. And observe that any linear combination of these things, say C1 times A1 by B1 plus C2 times A2 by B2 dot Cn times An by Bn, this belongs to the subgroup generated by 1 by B, because you can write down these things as in the denominator you can write it as a product of B1 up to Bn. Here it is C1 A1 times B2 to Bn plus C2 A2 times B1 to Bn except B2 and so on. You can write it, right? So above part is an integer divided by B. So that means it is inside this cyclic subgroup generated by 1 by B. So that means in particular Q plus is contained in cyclic subgroup generated by 1 by B, right? Now choose a prime P such that P doesn't divide P. You can do that because there are infinitely many primes, right? So, and by definition 1 by P also belongs to Q plus, right? That means 1 by P equal to C times P. That will imply P equal to P by C. Okay, that will imply P divides P. That's a contradiction, true or assumption. Hence Q plus is not finitely generated. Okay, go to the next one. Any infinite cyclic group has exactly 2 generators. So it is enough to show that any infinite cyclic group is basically isomorphic to Z. So you can do by definition like let G be a infinite, G be an infinite cyclic group. Okay, that means G is generated by some element A. This will imply G is generated by A inverse also. Okay, because you can write A power n as A inverse power minus n. So the same thing. So A and A inverse both are generator of G. If B be another generator of G, then we have G equal to cyclic subgroup generated by A as well as B, right? So that means B power some K equal to A as well as A power some n equal to B. So if we write down it, that means B power nk equal to B. That means B power nk minus 1 is identity, right? So will imply order of B is finite. But since G equal to this and G is infinite, this will imply order of B is infinite. That's a contradiction, right? Hence G has exactly two generators. Right. Question number 4. Let G be a group, N be a normal subgroup of G of order n. If GCD of n, uh, index, so order and index are co-prime, then n is unique subgroup of order n. So n is unique subgroup of order n. Solution. Let H be another subgroup of order n. Since n is normal, NH is a subgroup of G. Now order of NH is order of n times order of H by order of n intersection H, right? Now let order of G is K, order of n equal to order of H equal to n, order of n intersection H is D. Okay, let order of G mod n is D. Okay, right. Now order of NH is subgroup, right? So that means order of NH divides order of G, which will imply n square divided by D divides n square divided by D divides K. N square divided by D divides K. Again, D divides n. Okay, that means Pn divides K. Okay, Pn divides K. So that means K equal to PNL. K equal to PNL. Again, by this condition, K equal to NT. Right? K equal to NT. Okay. Means T equal to PL. Right? that will implies P divides T, and again from the given condition we have P divides N. That's a contradiction, since N and T are co-prime. So this happens if P equal to 1, and P equal to 1 means this will imply P equal to 1 means N equal to T. N equal to T. N equal to T means order of H intersection N is same as order of H, same as order of N. That will imply H equal to N. Hence H is unique or N is unique. It's just a computation. Okay. And so given any two groups G and H, let Hom G, H is set of all group homomorphism from G to H. If A is any abelian group, then show that Hom S3, A and Hom Z2, A are bijective. Okay. Observe that S3 mod A3 is isomorphic to Z2. Okay, so if phi is a homomorphism from Z2 to A, I can take a similar copy of phi as an map from S3 mod A3 to A, right? Because S3 mod A3 is isomorphic to Z2. And again we have S3 to S3 mod A3, the natural quotient map, right? I mean the natural map. If we take the composition, that will give me an homomorphism from S3 to A. Right? That means if you have any homomorphism from Z2 to A, this will give me an homomorphism from S3 to A. So clearly Hom Z2, A cardinality is equal to Hom S3, A. Now conversely, let we have a map from S3 to A homomorphism. Okay. Now suppose kernel F is either identity or S3 itself or A3. So if kernel F is identity, that means image F is isomorphic to S3, right? Which is not a subgroup of A because A is abelian, right? So that means this case is not possible. So kernel cannot be identity. Okay, if kernel is S3, that means image F fit to identity, that means F is trivial. So trivial homomorphism is there. Now if kernel is A3, that means S3 mod A3 is isomorphic to Z2, right? That means in particular we can say that if we have any map phi from S3 to A, this factors through a map from S3 to A3 to this one. Okay, so if we have phi here, we have free tilde here. That means for any map we get a map from this to this, because of the case that since A is abelian, so kernel must be such a normal subgroup such that quotient is abelian. So I don't want to use any kind of concept of commutator subgroup. If you already know the definition of a commutator subgroup, then you can already say by just seeing that, because but I don't want to I don't want to tell anything related to that, because uh, commutator subgroup is slightly advanced concept. So I think for a BSc student, since it is MSc entrance exam problem, you can do by just definition. So by using the definition, you can just get this, because in this case kernel is either identity or A3. So S3 mod A3 is isomorphic to Z2, so you will get a map from this to this. Okay, so hence both are bijective. Okay, next question. Let V be a vector space of all function from R to R. W is f belongs to B such that f of I is 0. There existed W prime subset of V such that V is W direction W prime. So let W prime equal to lambda such that lambda belongs to R, lambda times 1. So that means I am taking the constant function 1. I am taking linear span of constant function 1. Okay. Now see, take any f, right? I can write fx as fx minus f pi plus f pi times 1. So this one is gx plus hx. So gx equal to fx minus f pi. That means g pi is 0. That means g belongs to w. And hx is f of pi times 1. Okay, this belongs to w part. Okay, and let k belongs to w intersection w part. Okay, that means k of pi is 0, as well as k equal to some lambda times 1. Okay, that means this will imply k is constant lambda. So in particular k of pi is lambda, so by definition lambda is 0, so will imply k is identically 0 on R. That means intersection is 0, hence p equal to w direction w prime. Very simple one. Go to the next problem. Construct a linear operator T from R2 to R2 such that image of T is this. So in any question like this, that construct a linear operator satisfying some property, you will try to hold this property on basis element, because we know that for any linear operator it is enough to define that operator on basis, then it uniquely extends to a linear operator on whole space. That is the main thing about vector space and linear operators. So if you define properly on basis, that will be enough for you, right? So I want to define a linear operator so that this satisfies this on basis, and that will gives me a map from R2 to R2. Okay, that's the idea. So let T of 1, 0 is basically 1, comma minus 1, and t of 0 comma 1 basically 0. Okay, this is my definition. Then you can see that t of x comma y is basically t of x comma 0 plus t of 0 comma y, which is same as x comma minus x plus 0 comma 0, which is same as x comma minus x. So clearly image of t is xy such that x plus y is 0, and this is the linear operator. Okay. Now observe that dimension of image t is 1. Okay, here. Right, that's fine. But for B part, it says that for each n greater than 2, is it possible to construct such a function? So for n greater than 2, what about image t? Image t says that n tuple, okay, n tuple such that summation xi I equal to 1 to n is 0. It means dimension of image t is n minus 1. Okay, dimension of image t is n minus 1. Okay. So they ask that is it possible to construct such a map from R2 to Rn, right? So by definition, by diagonalization theorem, okay, so definition, not a definition, by diagonalization theorem, dimension of R2 is dimension of kernel T plus dimension of image T. That means 2 greater equal to at least n minus 1, right? So what you can do, so if the n is 3, okay, or if means 3 greater equal to n, that means n has to be less equal to 3. Okay, n has to be less equal to 3. So for n greater than 3, it is not clearly possible. Okay, it is not, it is not possible. Okay, for n greater than 3, it is not possible. What about n equal to 3? Okay, so if n equal to 3, so if n equal to 3, that means dimension of image 2 is 2, right? That means dimension of kernel T is 0. 3, that satisfies this condition. Okay. So that means what you can do in particular, not this map will not work. So this, okay, and what I don't think this will, okay, try to do it on basis. Okay, see this linear methods. This is an example. Okay, fine. Now the Question number 8. Let T from R2 to R2 be a linear map whose matrix representation with respect to some basis has off-diagonal entries with same sign. Okay. So let A be the matrix representation with respect to some basis. T with respect to some basis. So A equal to say A, B, C, D such that B and C has same sign. Okay. So I'll find the characteristic polynomial. AT minus BC. Now we want to find the roots, right? The solution. By 2, right? Which is same as A plus D plus minus root over A minus D square plus 4BC, right? Right? Now observe that B and C has same sign. That means BC always greater equal to 0. That means this part is greater equal to 0. That means lambda is real. Lambda is real. Okay. Now if so BC is always positive, right? BC is always positive. So if this is 0, if this is non-zero, then two roots are distinct, right? And if this is 0, that will imply A equal to T and B equal to C equal to 0, right? A equal to T and B equal to C equal to 0. So if two roots are distinct and the linear operators from R2 to R2, two roots are distinct, that means minimal polynomial has distinct roots. That means this is diagonalizable. That matrix A, B, C, D is diagonalizable. And if this is 0, that means A equal to D and B equal to C. That is a scalar matrix. That is also diagonalizable. So for both cases, the linear operator is diagonalizable. So for the both case, linear operator is diagonalizable, and that is the thing. Like, so when a linear operator is diagonalizable, that means the eigenvectors are linearly independent and they span the vector space V, right? So here R2 has a basis consisting of eigenvectors of T, since T is diagonalizable. Okay, so that's the simple computation, right? Now the last problem from algebra section, that let A be a n by n matrix with all diagonal entries equal to 1 and all of its off diagonal entries equal to A, not 1. I think I put some entries equal to A. So right. Then I need to show that determinant of A is this and find all the eigenvalues and eigenvectors. So if you find out the matrix representation and say if you find out the eigenvalues, then you can easily find the eigenvectors also. That is just a computation, right? So let A is a n by n matrix of all diagonal entry is equal to, so A, this is n by n, 1 A, 1 A, here this is 1, and all the other terms are A, right? Fine. Let A plus A minus 1 identity. Then it becomes what? And then it becomes a matrix with all entries A. So this matrix is B. Then A is basically B minus A minus 1 identity, right? Now what are the eigenvalues of A? B. What are the eigenvalues of B? So B is basically A, this A, right? Observe that okay, so I'm assuming A is non-zero. For A is 0, also do the same thing. Okay, I distinguish A to be A not equal to 0 and do this. You can do same for A equal to 0 also. Okay, so observe that rank of B if A is non-zero. Okay, if A is non-zero, if A is 0, then B is 0 matrix, right? If A is 0, B is 0 matrix, then we are easily done. But if A is non-zero, then rank of B is n minus 1. Sorry, rank of B is 1, and rank of B is 1, because you can just do A minus A, say last row minus the n minus 1th row, then you can do last row minus n minus 2th row, and so on. Then you will get, if you find the row echelon matrix, you will get that here this is say first row becomes say A, and all the other rows are 0. So rank of B is clearly 1. Okay, rank of B is clearly 1. That means B has at least n minus 1 eigenvalues which is 0, because kernel of B is n minus 1. So, and A algebraic multiplicity is greater or equal to geometric multiplicity. So that means eigenvalue 0 occurs at least n minus 1 times. It may occur n times, but we know a result. We know if sum of each row of a matrix is same, then that is an eigenvalue. It is quite simple to do, because say you have A11, A1n, such that each row has same sum of each row is same. You can multiply it, say 1 1 1 1 1. This is your eigenvector, and you can see that you will find that sum value, and say A11 up to A1n is k. So you can write it as k times 1 1 1 1 1. Hence k is an eigenvalue, and 1 1 1 1 1, this is an eigenvector corresponding to eigenvalue k. Hence this holds, right? This is true. So this is true for this B matrix also. That means B has an eigenvalue n lambda. Sorry, na, not n lambda, na. Okay, so that means eigenvalues of B na comma 0, all the others are 0. That means eigenvalues of A na minus A of minus 1. minus 1 times 1 minus a, 1 minus a. So determinant, product of eigenvalues, so that means 1 minus a power n minus 1 times 1 plus n minus 1. Okay, and you can compute the eigenvectors corresponding to this eigenvalue. Okay, this is easy computation. I don't want to do it because that makes a very lengthy video. Okay, I hope all the solution you understand. If you have any doubt, you can just comment, and please share this video so that many students can get help. Okay, I'll make the second part of this video to solve the analysis part question. Okay, thank you.